All right, hello everyone. I'm back for another video. This is 1.c.2. We're going to talk about the quantum mechanical model of the atom, the current model of the atom. There's some good news about it, there's some bad news about it. You'll probably be indifferent to both types of news. So let's get started. I'm going to jump off to the corner. I'm going to write the notes down. The good news is this is going to be a pretty short video because these are all of the notes, and you'll see why when you read that last sentence. But I don't want to ruin the surprise, so here I go. Okay, so let's talk about the quantum mechanical model of the atom. It turns out that the model that you're used to seeing, this guy right here, where, let me pick a different color, do a little green nucleus. You know this Lewis structure, where, oh look, here, this is carbon, yay, it's awesome, and it's 4 valence electron. That's great. This model of the atom is actually a little bit on the old side. The quantum mechanical model was actually developed in the 1960s, so this one model of the atom came around kind of the 30s. We talk about Niels Bohr and all that stuff. So, it's really kind of an antiquated model. However, there's some really important reasons why we use it. There's some really important tools that we can use with it. But let's talk about the newest model. Without getting into too much detail, there's something called the Standard Model of Particle Physics. And that's where people start dealing with quarks and neutrinos and neurons and all those other subatomic particles. We're not going to get into any of that because that's well beyond the scope of this class. But the quantum mechanical model is kind of fringing on that. So, we talked about orbitals. What happens is electrons orbit the nucleus in very non-set routes or non-distinct patterns. They kind of just randomly fly around there, random-ish. And they tend to move in a wave pattern, right? Because some fun thing in physics is that most things move as a wave. I don't understand it, but maybe you will. We call where they move called the orbital, so where the electrons generally are. And in previous videos, I've talked about how it's really only where they are 95% of the time. They can be slightly outside the orbital because these are clouds. They're called electron clouds because the edges are fuzzy and hazy. Okay, so a couple of factoids about orbitals. Orbitals contain 2 electrons max, and you might be like, Mr. Wood, what about the p orbital? That has 6. And I'd be like, ooh, good question, student. So let's say we have the p orbital. Like, let's just say the 2p orbital, right? It can have up to 6 electrons. Well, it turns out that it doesn't really have up to 6 electrons. There's actually 3 orbitals in there. There's 2p sub x, 2p sub y, and 2p sub z. But now hopefully x, y, and z, you're thinking, you're like, whoa, wait a second. I've seen that combination of variables before. Turns out that those are the axes, axi, that those orbitals are found on. So I'm only going to do 2 of them because I can only draw 2 of them. The p orbital is shaped like a dumbbell. This is 2p sub y. Look at that. Oh, look what axis it's on. It's on the y-axis of a graph. It's crazy. Here is another 2p orbital. That's 2p sub x. Notice it's on the x-axis of the graph. And now you might be realizing why Mr. Wood's not going to draw the z1 because the z1 goes into the board and out at you. And I am not that good. Okay? I know my limitations, and it is 2-dimensional graphing. Alright, so that's what we mean by they contain 2 electrons max. Remember, these electrons repel each other. So anytime an electron is up here, that's a horrible color. Let me do green. That's a super pretty color. Anytime I have an electron up here, I'm going to have the other electron down here. Right? They're always going to be opposite each other. Anytime I have an electron over here, they're going to be over here. Now remember, they're moving ridiculously fast. So they are kind of moving around pretty quick. So every orbital can have 2 electrons max. And then we combine these to kind of like the p orbital. The p orbital has 3 suborbitals that contain 2 electrons max. Now within that, these electrons have something called a spin. The property of spin we denote by the arrows. Now if you guys remember, maybe way back when in honors chemistry you did a worksheet called Camp Bulldog. You might remember you had to assign students, campers, their electrons, to different cabins. Do you guys remember drawing up arrows and down arrows? For whether they're in the top bunk or the bottom bunk? That's crazy. Alright? Take a look. If you have no clue what I'm talking about, then this is going to make no sense, but that's okay.
So here's the 2p orbital. Notice there's 3 suborbitals, and each suborbital can take 2 electrons. One with what's called an upspin and one with what's called a downspin. Spins on electrons is what makes elements magnetic or not. Alright, so things like iron, iron's magnetic because of the spin of the electrons. And I'm not going to get into it any farther than that, because honestly it's been a while since someone's talked to me about electron spins, and I don't want to say anything that's wrong. All I know is that it has to do with magnetism, and you need an odd number of spins, so you have more ups than downs, or more downs than ups, and it makes it positive or negative or whatever. But don't worry about that. Quantum models. Here's the great news about the quantum model. It is complex. There's a lot to it. And generally you need a computer to compute or generate this quantum model of the atom. There's way too much going on. There's too many variables for us to do it in class on any of our computers, let alone in class on a sheet of paper or anything like that. People don't do it. Therefore, we are going to use the antiquated Bohr model of the atom. The important thing is not that it's antiquated, because it's a great, simple representation of the atom. The important thing is for you to realize that it is not the current model. It is close to the current model, but it's not the current model. It works well for everything we're going to worry about in this class, but later on, when you go on to upper level chemistry, it falls apart. And that's fine, because when you get into upper level college chemistry, then you'll worry about the quantum mechanical model. In here, in this AP chemistry class, we're going to deal with the Bohr model. Okay? The Bohr model is the model of the atom where I have a central nucleus, and then I have orbitals extending out from that central nucleus. Alright, so this element right here, that's a nucleus, that's an electron, that's hydrogen, 1 electron. Check it out. Boom. Helium. 2 electrons. Notice I didn't change the nucleus. I'm not like adding neutrons on there. That's crazy town. Alright? That's my sound for drawing new orbitals. That, lithium. Great job. Hey look. That's beryllium. Almost said magnesium. That would have been embarrassing. That's beryllium. Alright? Check it out. Boron. Carbon, and so on, and so on, and so on. That's the Bohr model of the atom. I'm not going to go up to like 118, octium, because I'm not insane. Alright, so hopefully that's cleared it up. I know I didn't give you much information at all. I'm pretty much saying that there is something called the quantum mechanical model. It is crazy complex, crazy confusing, and you don't have to worry about it, because we're going to use the Bohr model of the atom, which was generated like 60, 70 years ago. But that's okay. I'm okay with it. You should be okay with it. All right, have a wonderful day, and I will see you tomorrow in class.